What's the difference from a software perspective or between AI and neural network-based systems and normal software?
Yeah. So a good way of bundling that together would be using the term machine learning. So yeah, if we have to take, let's look at this picture. You have what is called machine learning. Then under machine learning, you have what is called deep learning. Then under deep learning, you have what is neural network. Machine learning as a whole is still, that is an AI, is a form of AI. Holistically, it's just you trying to build that system that has intelligence based off of data. So using usually statistical approaches that are based on data. Then when you take neural networks or deep learning, then the focus is more of something that has borrows a lot from the biological brain of a person.
Okay.
Now, if you are comparing that to software development, a good way to look at deep learning is that, or even machine learning as a whole, it's software development 2.0. Or sometimes people call it, for those who are excited in the math, sometimes they call it differential programming because there's a lot of differential calculus involved. But the idea is that for software, the normal software that programmers build, what you usually do is that you want to build something that will take inputs either from users or from another system and then generate outputs that is similar across. So let's say flights, let's say, what's the name? So planes, right? The way planes work, they are complex autopilot softwares that actually program the rules of what it takes to drive an aeroplane. And so you have these rules that are executed. They are rules that a human being wrote. And so you execute the rules and then things happen according to the rules. If anything you should encounter deviate from the rule, your system will not be able to handle it. So that's one of the things about software development. And so one thing, it means that you have to be able to account for all possible inputs. You have to know all rules that fit every input. So account for all possible inputs. And the second one is you should know all the rules. So if you want to build a system to allow a plane to fly itself, you have to know all the rules that are involved in building an aeroplane or flying an aeroplane. If you want to do the same for cars, you have to account for all the rules.
In other words, you have to anticipate all possible scenarios.
Exactly. You have to anticipate all possible scenarios. And if you ever find yourself trying to build for a situation where it's near impossible to anticipate for all possible scenarios, then it's difficult to use the normal or classical software development approach. So an example like self-driving cars, you cannot account for all the rules that are driving them because it could be, yes, a human being standing before you, but what does even a human being look like? If it's a human, if you define it as someone with short hair, and then someone like myself comes around with a lot of bushy hair, your system will not be able to handle that. And if someone comes with dreadlocks, someone comes with
no hair like mine,
all that, you have to account for all. Exactly, no hair. So there are too many scenarios that you wouldn't be able to, and that's just human hair. That we haven't started talking about rabbit, chicken, goats. You know, in our side of the world, anything can be on the road. So it makes it impossible to use that approach. So this is where machine learning comes in. If machine learning is also doing the same thing, you have some inputs and you have outputs, and you're trying to build something that will let you process the inputs and give you the right output you want. The advantage of machine learning is that you don't have to know all the rules. All you need to do is that get enough data, usually enough data of the inputs and enough data of the outputs. If you give this machine learning system, you give it to this deep learning system, and you have enough example of the input and output, it will be able to learn the rule on its own. So it's basically like software development, but instead of you building a program to do something or you knowing the rules, the AI system itself will learn the rules or will generate a program based on the data you provide.
So what we are saying is that if you're talking about addition, for example, in classical software development, I have to put the rules that x plus y is equal to this. So every time I have s, if s is 2, if it's 2 plus 2, the answer will be 4. If it's 2 plus 3, the answer will be 5. But in machine learning, what I will do is that I will show the software maybe 1 and another 1. I will not put the sign, the plus sign in between, and then show the software the final answer. I will keep showing the software enough examples of additions without telling you the actual rule in between, so that eventually the software will figure out that if you this plus this is the sort of output that is expected. Is that it in a nutshell?
Exactly. That's the general. Yeah, that's exactly the idea behind it. And if you look at that in itself gives you a lot of insight. So the question is it reasonable to collect a lot of examples of addition with their answers and then give it to an AI system to learn? Or is it easier to just say X plus Y generate outputs? So that in itself determines that there are different problems for different approaches. So it's not necessarily like AI is coming to replace the normal software development. Is that there are certain problems that the rules are very simple and clear. So addition has very simple and clear rules. You don't need to worry about collecting data on it. But there are problems that have too many scenarios, have too many possible angles. Exactly, that you cannot be able to account for them. So for those ones, collect data on them and have an AI system learn.
So that means that
it's more of another toolkit to add to software development.
Okay, now this is my problem with AI. Clearly, from what you said, it is more suitable for variable situations with unpredictable context or outcomes. However, because it's basically a black box, all right? If I'm doing traditional software, I'm actually telling the software explicitly in situation A, do B, situation C, do D. But with the AI coding, you're basically showing the software input and output, and it should not figure out the operation in between. Now, that has a problem when it comes to debugging the software. Because the system has figured out, okay, if you're talking about self-driving, in this context, this is normally how you're supposed to behave. But what about if it came to the wrong conclusion? How can I go within this black box and tweak a particular variable so that the output will be corrected? I don't know whether you understand that, what I'm trying to.
Yeah, that's definitely. Oh yes, it's definitely a major challenge in deep learning. So an example being that you want to between cats and dogs, and then you collect your data and then you feed it into your AI system, and then you test your AI system on that data, and you realize your AI system scored 99%. So you concluded that my AI system is very good at differentiating between cats and dogs. But then you later realize that no, all the images of the cats were taken
white cats
in a lawn or in the background with grasses on it. Then all the images of dogs were taken on concrete.
Okay.
So your AI system did not learn the difference between cats and dog. It simply learned the difference between color green and then gray in concrete. Okay. So it concluded that anytime I see green, I should say that's cat. And anytime I see gray, I should say dog. It just so happens that there were cats and dog also in those images. So that's definitely a challenge. There are a lot of approaches that we use to address this. Data is almost the important thing. The first thing you should do is that you should ensure that your data is a strong representation of reality. So if you want cats and dogs, you should be able to have photos of cats and dogs in a lot of different backgrounds as possible. Different cats as well. If you are looking at diseases, you should have them across different demographics. So if you are looking at something like breast cancer, you shouldn't just take one demographic from, say, Accra or Lagos. You should be able to, if you want your AI system to be used around the world, you should collect data as far as breast cancer is concerned from around the world, different ethnicities, different age groups, different conditions. So someone might have breast cancer, but also as much variation as possible before you feed it to an AI system. There are several techniques that attempt to see if there's truly variation within your data. The other approach is also testing your generalization of your AI system. So if you want to test that, okay, your AI system actually doesn't only perform well on data that you train it on. A good example is that if you collect data and then you build an AI system with that data, yes, you can take part of that data out and use to test your AI system, but that is not enough testing. You should also go out there, an entirely new location that you haven't probably explored yet, and go collect absolutely new data from there, and then use that data to test your AI system again. There are multiple ideas. So take, for example, Tesla uses this idea where they frame their AI system in a way that whenever a human being makes a decision whilst driving, they also give that input to the AI system to see what decision the AI takes. If the decision the AI takes is different from the decision that the human takes, that means that there's some disagreements. That doesn't mean the AI system did not perform well. In that case, those scenarios are sent back to the developers, and then they use those scenarios to better improve the AI system. So yeah, there are a few number of technical approaches. Even further, you can actually look within an AI system. So yes, it's true, we call them black boxes, but it's not as if we can't tell what's within it. There are approaches, some of them are called LIME. It has something to do with local model invariance. I can't remember the full term now, but there's an approach that is developed that allows you to actually look within a neural network to tell that, okay, what is actually going on here. So an example being that we have these things that are called region of interest. So if you wanted to, or in some cases, you also have activation maps. So if you wanted to see your AI system's performance on cat and dog, using some of these approaches, you could ask your AI system to highlight in an image, yes, of the animal within the photo. As one of the strongest reasons why it's concluded that this is a cat, we know the shape of cat's ears and dog ears are different. If you highlighted the tail, the head shape, the AI system, instead of focusing on the animal, start focusing on the background, then you realize that, okay, your AI system is not making decisions, whether it's cat or dog, based on ears, fur, and all those things. It's making those decisions purely based on the background. So yeah, there are a number of technical approaches to help us address this problem.
Okay, so since you brought up self-driving cars, from your presentation, it's clear that data is very important for training AI systems. And not only that, the more realistic the data is, the more relevant it is, and also the more variable it is. I've observed that a lot of, in the AI space, it seems to be kind of tribal. So like you, because you're in Africa, most of your training data sets are coming from Ghana or Africa. Tesla and Co, for example, what they are doing, when you look at the map of their car, you see that most of their training data sets for their AI systems is coming from Europe, China, and America, where their products are. It's only companies like Google and Amazon and Apple who have a global reach that there's enough variability. How do we bridge that challenge?
Yeah, so actually, there's the funny thing is that it's easier for me to get data from the US than to actually get data from Ghana. So that is a funny thing there. Unfortunately, we don't have systems in our side of the world that prioritizes data collection. So getting some data is not really that easy in Africa. So yeah, we are dependent on mostly data from the US, data from the UK.
So what you are saying is that
As far as
we can actually have you can develop a system, for example, that before you realize the training data set is coming from, let's say, UK. So it may not even be localized for our problems or situations here.
yes, yes. Or sometimes in our team, what we actually end up doing is that we will have data that might be mostly, it depends. If it's for research, sometimes you just point out, oh, this is data from the UK, this is data from the US, and that's okay. But if you are building systems to be used in a local scenario, what we end up doing sometimes is that you take the UK data as UK US data from around the world as much as you can get. Then you also try your best to get as much local data as possible. The idea is that these things are similar in a lot of ways and they are different. So if you take, for example, pneumonia, you can detect pneumonia from looking at x-rays of the chest. There might be a lot of variation across demographics, a lot of ethnicities, but the demographics or the variations are not large enough. So if you collected enough data from the UK, the US, and you collect some amount of data from the local ones, your AI system will first of all learn generally what pneumonia looks like on the chest. But because you've added that local data, your AI system has also learned what pneumonia variations in West Africa or in Ghana or in Africa might also look like. So yeah, it's a very
That's a very roundabout way of doing things.
Exactly. You have to be hackish about it. But yeah, some people also use this. So what's the name? Comma AI also uses a similar approach, which is that good drivers are similar in more ways than they are bad. So in a sense that if you capture a lot of data from different people driving, instead of you trying to say, let's get good drivers and then train these good drivers to drive in a way that I want AI to just learn from, if you have enough examples of just drivers driving, your AI system is a bit of a hackish shooter approach. But then basically what they are doing is that if you collect enough data, your AI system is able to just learn generally that, okay, these are good driving, even though there'll be a lot of bad driving in it that you exceed out. And then if there's any variation in driving, so if someone drives with a specific style or something like that, that is captured as an additional feature, an additional rule. It's not seen as the base form of driving. It's just seen as an additional rule. So yeah, there are ways of going about it. But to actually come back to your original question about achieving that generalized AI system, there are a few ways to go about it. So first of all, the question is that, do you want to build an AI system to be used globally, or do you want to build an AI system, at least in the first version, to be used locally? So if you want to build an AI system to be used only in Ghana, maybe you don't need to wait to get data from every single country or every single continent before you deploy in Ghana. You can mainly ensure that you have enough data from Ghana and then maybe other West African countries. Then maybe also capture additional data from other parts of the world. So actually one of the systems that I have, so there's a platform that I worked on under our UN work. So this is an approved framework and platform. It's called Precision Evaluation. The whole idea is that if you want to deploy an AI system in Ghana, you can have this platform tell you how ready your AI system is for in Ghana, as opposed to how ready your AI system is to be used in, say, Morocco or, say, China, based on the testing data. So if you are testing with purely Ghanaian data, your AI system performs this well. But if you try to move it to another geographical area, even if you expand it to the rest of West Africa, this is how well your AI system performs. So it's more of seeing how well you scale your AI system. So back to the software development comparison. in software development, if you build something that can calculate numbers, right? It doesn't matter. You could deploy it anywhere in the world. You could scale. You could start from Ghana. If you have enough money and whatnot, you could scale to other parts of the world with the same software. It's a calculating platform. That's it. But for AI STEM, if you want to scale beyond Ghana, wherever else you want to scale to, you need to collect data from that location. So that is one approach to it. Another possible angle to that question is that we have open source data or we have publicly available data. So not everyone does data and hide it to themselves. You have, for chest conditions like this, there's data from UK and there's data from the US. This data have been published and then people use it globally. So you have this sort of global data or people making available data from their part of the world. So if you're an AI developer and you want to build an AI system in Ghana, you could gather data from around the world. That is also an option.
Anyway, thank you very much.
But yeah, last final point is that nonetheless, it's a problem. It's a problem.
How did you get into this space? I mean, how did the Ghanaian boy, what's your AI story?
Sure. Yeah. So I'm quite a radical. At least my beginning was very much radical. So to talk about my beginning in AI, I also need to include my beginning in computer science and to some degree my deviation away from education. So I've been fortunate enough to be programming computers since age 14.